Welcome friends. In the last session, we have seen the basic terminology used in graph theory. The basics of multigraphs, weighted graphs, paths and circuits were also discussed. Two important types of graphs, namely the Eulerian and the Hamiltonian graphs, were also introduced. This session covers special properties of planar graphs. Graphs and planar graphs, Part 2. A planar graph is a graph which can be drawn in the plane without any edges crossing. We have understood that even though some pictures of a planar graph might have crossing edges, it is possible to redraw the picture to eliminate the crossings. For example, although the usual pictures of the complete graph K4 and the cubical graph Q3 have crossing edges, it is easy to redraw them so that no edges cross. For example, a planar picture of Q3 is shown on the screen. However, if you fiddle around with drawings of the bipartite K33 or K5, there does not seem to be any way to eliminate the crossings. We will see how to prove that these two graphs are not planar. Planar graphs have some interesting mathematical properties. Example, they can be colored with only 4 colors. Also, as we will see later, we can use facts about planar graphs to show that there are only 5 platonic solids. There are also many practical applications with a graph structure in which crossing edges is a problem, including design problems for circuits, subways, utility lines, etc. Two crossing connections normally means that the edges must be run at different heights. This isn't a big issue for electrical wires, but it creates extra expense for some types of lines, like burying one subway tunnel under another and therefore deeper than you would ordinarily need. Circuits in particular are easier to manufacture if their connections live in fewer layers. Phases. When a planar graph is drawn with no crossing edges, it divides the plane into a set of regions called phases. By convention, we also count the unbounded area outside the whole graph as one phase. The boundary of a phase is the subgraph containing all the edges adjacent to that phase, and a boundary walk is a closed walk containing all of those edges. The degree of the phase is the minimum length of a boundary walk. For example, as the figure shown on the screen, the first graph has 3 phases. The boundary of phase 2 has edges DF, FE, EC, CD, so this phase has degree 4. The boundary of phase 3, that is the unbounded phase, has edges BD, DF, FE, EC, CA, AB. So, phase 3 has degree 6. The second graph of figure shown on the screen has a spike edge sticking into the middle of phase 1. The boundary of phase 1 has edges BF, FE, EC, CD, CA and AB. However, any boundary walk must traverse the spike twice. Example, one possible boundary walk is BF, FE, EC, CD, CD, CA and AB, in which CD is used twice. So, the degree of phase 1 in the right hand graph is 7. Notice that the boundary walk for such a phase is not a cycle. Now, let us consider another example. The figure shown on the screen with 6 vertices and 9 edges divides the plane into 5 regions. Observe that 4 of the regions are bounded, but the 5th region outside the diagram is unbounded. Observe that the border of each region of a map consists of edges. Sometimes the edges will form a cycle, but sometimes not. For example, in the figure shown, the borders of all the regions are cycles except for R3. However, if we do move counterclockwise around R3, starting say at the vertex C, then we obtain the closed path C, D, E, F, E, C, where the edge E, F occurs twice. We note that each edge either borders 2 regions or is contained in a region and will occur twice in any walk along the border of the region. Thus, we have a theorem for the regions of vertices. Theorem: the sum of the degrees of the regions of a map is equal to twice the number of edges. The degrees of the region of the figure shown are: degree of R1 is 3, degree of R2 is 3, degree of R3 is 5, degree of R4 is 4 and degree of R5 is 3. The sum of the degrees is 18, which as expected is twice the number of edges. For notational convenience, we shall picture the vertices of a map with dots or small circles, or we shall assume that any intersections of lines or curves in the plane are vertices. Let us see the proof of Euler's theorem. Finally, for connected planar graphs, we have Euler's formula V minus E plus F is equal to 2. We will prove that this formula works. Suppose the connected map M consists of a single vertex P as shown in the figure. Then V is equal to 1, E equal to 0 and R is equal to 1. Hence, V minus E plus R is equal to 2. Otherwise, M can be built up from a single vertex by the following two constructions. Add a new vertex Q2 and connect it to an existing vertex Q1 by an edge which does not cross any existing edges as shown in the figure. Connect two existing vertices Q1 and Q2 by an edge E which does not cross any existing edge as in figure. Neither operation changes the value of V minus E plus R. Hence, M has the same value of V minus E plus R as the map consisting of a single vertex, that is V minus E plus R is equal to 2. Thus, the theorem is proved. Now, let us see some corollaries of Euler's formula. Corollary 1. Suppose G is a connected planar graph with V nodes, E edges and F faces where V is greater than or equal to 3. Then E is less than or equal to 3V minus 6. The proof is like this. The sum of the degrees of the faces is equal to twice the number of edges, but each face must have degree greater than or equal to 3. So, we have 3F is less than or equal to 2E. Euler's formula says that V minus E plus F is equal to 2. So, F is E minus V plus 2 and thus 3F is equal to 3E minus 3V plus 6. Combining this with 3F less than or equal to 2E, we get 3E minus 3V plus 6 is less than or equal to 2E. So, E is less than or equal to 3V minus 6. We can also use this formula to show that the graph K5 is not planar. K5 has 5 nodes and 10 edges. This is not consistent with the formula E less than or equal to 3V minus 6. Unfortunately, this method won't help us with K33, which is not planar but does satisfy this equation. We can also use this corollary 1 to derive a useful fact about planar graphs, which is given as corollary 2. If G is a connected planar graph, G has a node of degree less than 6. Let us see the proof. This is clearly true if G has 1 or 2 nodes. If G has at least 3 nodes, then suppose that the degree of each node was at least 6. By the handshaking theorem, 2E equals the sum of the degrees of the nodes. So, we would have 2E greater than or equal to 6V. But corollary 1 says that E less than or equal to 3V minus 6. So, 2E is less than or equal to 6V minus 12. We can't have both 2E greater than or equal to 6V and 2E less than or equal to 6V minus 12. So, there must have been a node with degree less than 6. If our graph G is not connected, the result still holds because we can apply our proof to each connected component individually. So, we have the next corollary. If G is a planar graph, G has a node of degree less than 6. When all the cycles in our graph have at least 4 nodes, we can get a tighter relationship between the number of nodes and edges. Corollary 4. Suppose G is a connected planar graph with V nodes, E edges and F faces where V is greater than or equal to 3 and if all cycles in G have length greater than or equal to 4, then E is less than or equal to 2V minus 4. Let us see the proof. The sum of the degrees of the faces is equal to twice the number of edges, but each face must have degree greater than or equal to 4 because all cycles have length greater than or equal to 4. So, we have 4f less than or equal to 2e, so 2f is less than or equal to e. Euler's formula says that v minus e plus f is equal to 2, so e minus v plus 2 is equal to f. So, 2e minus 2v plus 4 is equal to 2f. Combining this with 2f less than or equal to e, we get that 2e minus 2v plus 4 is less than or equal to e. So, we have e less than or equal to 2v minus 4. This results lets us show that K33 is not planar. All the cycles in K33 have at least 4 nodes, but K33 has 9 edges and 6 nodes, which is not consistent with this formula. So, K33 can't be planar. Now, let us see the famous theorem, Kuratovsky's theorem. The two examples of non-planar graphs K33 and K5 were not picked randomly. It turns out that any non-planar graph must contain a subgraph closely related to one of these two graphs. Specifically, we will say that a graph G is a subdivision of another graph F if the two graphs are isomorphic, or if the only difference between the graphs is that G divides up some of F's edges by adding extra degree 2 nodes in the middle of the edges. For example, in the figure shown on the screen, the right hand graph is a subdivision of the left hand graph. For many years, mathematicians tried to characterize planar and non-planar graphs. This problem was finally solved in 1930 by the Polish mathematician K. Kuratowski. The theorem is like this: a graph is non-planar if and only if it contains a subgraph that is a subdivision of K33 or K5. This was proved in 1930 by Kuratowski, and the proof is apparently somewhat difficult. So, we will just see how to apply it. For example, here is a graph given on the screen, which is known as the Petersen graph after the Danish mathematician named Julius Petersen. This is not planar. The offending subgraph is the whole graph except for the node B and the edges that connect to B. This subgraph shown in the figure is a subdivision of K33. To see why, first notice that the node B is just subdividing the edge from D to E, so we can delete it, or formally the previous graph is a subdivision of this graph. In the same way, we can remove the nodes A and C to eliminate unnecessary subdivisions as shown in this figure. Now, deform the picture a bit and we see that we have K33 as the figure shown on the screen. Now, let us see coloring of planar graphs. One application of planar graphs involves coloring maps of countries. Two countries sharing a border must be given different colors. We can turn this into a graph coloring problem by assigning a graph node to each country. We then connect two nodes with an edge exactly when their regions share a border. This graph is called the dual of our original map. Because the maps are planar, these dual graphs are always planar. Planar graphs can be colored much more easily than other graphs. For example, we can prove that they never require more than 6 colors. Let us prove this by induction on the number of nodes in G. The planar graph with just one node has maximum degree 0 and can be colored with one color. The induction is like this. Suppose that any planar graph with k nodes can be colored with 6 colors. Let G be a planar graph with k nodes. Now, by corollary 3, G has a node of degree less than 6. Let us pick such a node and call it V. Remove some node V and its edges from G to create a smaller graph G dash. G dash is a planar graph with k minus 1 nodes. So, by the inductive hypothesis, G dash can be colored with 5 colors. Because V has less than 6 neighbors, its neighbors are only using 5 of the available colors. So, there is a sparse color to assign to V, finishing the coloring of G. It is a bit hard to upgrade this proof to show that planar graphs require only 5 colors. 4 colors is much harder. Way back in 1852, Francis Guthrie hypothesized that any planar graph could be colored with only 4 colors, but it took 124 years to prove that he was right. Alfred Kempe thought he had proved it in 1879, and it took 11 years for another mathematician to find an error in his proof. The 4-color theorem was finally proved by Kenneth Apel and Wolfgang Haken in 1976. They reduced the problem mathematically, but were left with 1936 specific graphs that needed to be checked exhaustively using a computer program. Now, let us see a theorem. The following are equivalent for a graph G. G is 2-colorable, G is bipartite, every cycle of G has even length. Let us see the proof now. 1 implies 2 goes like this. Suppose G is 2-colorable. Let M be the set of vertices painted the first color and let N be the set of vertices painted the second color. Then M and N form a bipartite partition for the vertices of G, since neither the vertices of M nor the vertices of N can be adjacent to each other since they are of same color. 2 implies 3 goes like this. Suppose G is a bipartite and M and N form a bipartite partition of the vertices of G. If a cycle begins at a vertex U of say M, then it will go to a vertex of N and then to a vertex of M and then to N and so on. Hence, when the cycle returns to U, it must be of even length. That is, every cycle of G will have even length. Now, the proof for 3 implies 1. Lastly, suppose every cycle of G has even length. We pick a vertex in each connected component and paint it the first color, say red. We then successively paint all the vertices as follows. If a vertex is painted red, then any adjacent vertex to it will be painted the second color, say blue. If a vertex is painted blue, then any vertex adjacent to it will be painted red. Since every cycle has even length, no adjacent vertices will be painted the same color. Hence, G is 2-colorable, and thus the theorem is proved. There is no limit on the number of colors that may be required for a coloring of an arbitrary graph, since, for example, the complete graph Kn requires n colors. However, if we restrict ourselves to planar graphs, regardless of the number of vertices, 5 colors suffice. The minimum number of colors required to color a graph is called its chromatic number. Now, let us see an application on Platonic solids. A fact dating back to Greeks is that there are only 5 Platonic solids: cube, dodecahedron, tetrahedron, icosahedron and octahedron. These are convex polyhedra whose faces all have the same number of sides k and whose nodes all have the same number of edges going into them d. To turn a Platonic solid into a graph, imagine that it is made of a stretchy material. Make a small hole in one face, put your fingers into that face and pull sideways, stretching that face really big and making the whole thing flat. For example, an octahedron, that is 8 triangular sides, turns into the graph shown. Notice that it still has 8 faces, one of each face of the original solid, each with 3 sides. Graphs of polyhedra are slightly special planar graphs. Polyhedra are not allowed to have extra nodes partway along edges, so each node in the graph must have degree at least 3. Also, since the faces must be flat and the edges straight, each face needs to be bounced by at least 3 edges. So, if G is the graph of a Platonic solid, all the nodes of G must have the same degree d greater than or equal to 3, and all faces must have the same degree k greater than or equal to 3. Now, let us do some algebra to see why there are so few possibilities for the structure of such a graph. By the handshaking theorem, the sum of the node degrees is twice the number of edges. So, since the degrees are equal to d, we have d into v is equal to 2 into e, and therefore, v is equal to 2e by d. By the handshaking theorem for faces, the sum of the face degrees is also twice the number of edges. That is, k into f is equal to 2 into e. So, f is equal to 2e by k. Euler's formula says that v minus e plus f is equal to 2. So, v plus f is equal to 2 plus e, which is greater than e. Substituting the above equations into this one, we get 2e by d plus 2e by k is greater than e. Dividing both sides by 2e, 1 by d plus 1 by k is greater than half. If we analyze this equation, we discover that d and k cannot both be larger than 3. If they were both 4 or above, the left side of the equation would be less than or equal to half. Since we know that d and k are both greater than or equal to 3, this implies that one of the two is actually equal to 3 and the other is some integer that is at least 3. Suppose we set d to be 3. Then the equation becomes 1 by 3 plus 1 by k is greater than 1 by 2. So, 1 by k is greater than 1 by 6, which means that k cannot be any larger than 5. Similarly, if k is 3, then d cannot be any larger than 5. This leaves us only 5 possibilities for the degrees d and k. They are 3 3, 3 4, 3 5, 4 3 and 5 3. Each of these corresponds to one of the Platonic solids. Now, let us see how to represent graphs in the computer memory. There are two standard ways of maintaining a graph G in the memory of a computer. One way, called the sequential representation of G, is by means of its adjacency matrix A. The other way, called the linked representation or adjacency structure of G, uses linked lists of neighbors. Matrices are usually used when the graph G is dense, and linked lists are used when G is sparse. A graph G with m vertices and n edges is said to be dense when m is O of n square and sparse when m is O of n or even O of n log n. Regardless of the way one maintains a graph G in memory, the graph G is normally input into the computer by its formal definition, that is, as a collection of vertices and a collection of pair of vertices, that is edges. Adjacency matrix. Suppose G is a graph with m vertices and suppose the vertices have been ordered, say V1, V2 etc. to Vm. Then the adjacency matrix A, Aij of the graph is the m by m matrix defined by Aij is equal to 1 if Vi is equal to Vj and 0 otherwise. The figure shown contains the adjacency matrix of the graph G where the vertices are ordered A, B, C, D, E. Observe that each edge Vi, Vj of G is represented twice by Aij is equal to 1 and Aji is equal to 1. Thus, in particular, the adjacency matrix is symmetric. The adjacency matrix A of a graph G does depend on the ordering of the vertices of G, that is, a different ordering of the vertices yield a different adjacency matrix. However, any two such adjacency matrices are closely related in that one can be obtained from the other by simply interchanging rows and columns. On the other hand, the adjacency matrix does not depend on the order in which the edges, that is the pair of vertices, are input into the computer. There are variations of the above representation. If G is a multigraph, then we usually let Aij denote the number of edges Vi, Vj. Moreover, if G is a weighted graph, then we may let Aij denote the weight of the edge Vi, Vj. Now, let us summarize what we have learned in this session. We have tried to understand more about the planar graphs. We discussed the proof of Euler's theorem and saw some corollaries of it. We have seen some results in graph coloring and applications in Platonic solids. We have also seen an example of applying Kuratowski's theorem. We have learned how to find the adjacency matrix of a given graph. Now, let us see some assignment problems. First one, draw a planar representation if possible of the graphs A, B and C shown in the figure. Second one, Let G be a finite connected planar graph with at least 3 vertices. Show that G has at least one vertex of degree 5 or less. Third problem, find the adjacency matrix A of each graph shown in the figure. Fourth problem, draw the graph corresponding to each of the adjacency matrix given. Fifth one, find the minimum number n of colors required to paint each map shown in the figure. The following books are suggested for further reading. First one, Elements of Discrete Mathematics by C.L. Liu, Tata McGraw-Hill Publishing Company Limited, 2nd edition. Second one, Introduction to Graph Theory, Robin J. Wilson, 4th edition, Addison Wellesley, Longman Limited. Third one, Graph Theory with Applications by J. A. Bondi and U.S.R. Murthy, American Elsevier, 1979. Another one is Discrete and Combinatorial Mathematics, an Applied Introduction by Ralph P. Grimaldi, Pearson Education, 4th edition. Thank you for watching this program. We will continue our discussion with another topic in the next session. Till then, goodbye.